see if I can.
Let me just highlight a few things about Lenore. So, I mean, she's a long-time researcher in math and theoretical computer science. Her early work in model theory, but let me highlight her work in complexity theory over the reals. And defining models for that, and also really well known for her work on getting women and girls involved in math and science. I think founder of the Association for Women in Mathematics. Is that right? Yeah, I think so. And So pretty soon, I think pretty soon everyone and their mother is going to be interested in doing consciousness. For now, it's particular ones. So.
Okay. Let's see. I'm going to get this up here. So can you hear me? Yeah. So first of all, I want to say that I hadn't heard Manuel's talk. And somehow this is kind of crazy. We're working day and night together, but he was hiding on the side, preparing this talk for a while, very similar to my talk. So you're going to get some things twice. But hopefully, I should have had another hour to edit my talk down, and I just edited it up because I want to give some other parts. Okay, so today is Avram's 60th birthday. And it's kind of emotional for me because I'm going to go back to his 0th birthday, which was exactly 60 years ago today. May 27, 1966. Okay. And let me say, it was a very nice spring day like today. I was in Cambridge, actually. I was a graduate student of mathematics at MIT then. And that year, I was the head TA for a fantastic course that Hartley Rogers was giving on model theory. This is building 2. All the buildings at MIT have numbers, and this is the math department, and here's Hartley Rogers, who was teaching that class. And I was just realizing, in those years also, logic was a big thing. I mean, Hartley's class was huge. I was a head TA of a graduate course. And in fact, John's dad was, Gene, was in my class, and I knew him very well. He was that's John Kleinberg, and Gene Kleinberg was in that class. He actually was an undergraduate, one of the undergraduates in this graduate course. So we go way back, way back. This is 60 years ago. Okay, so it's May 27th, so we had exams, and so I was up in building 2. Oops, I'm just getting a little ahead of myself, but let me go backwards. Okay, we're going to go back. So we're grading finals, actually, in Hartley's. I'm up there on the 2nd floor of building 2, and it's the afternoon. And about 1 o'clock, I'm feeling this kind of tightening or something. I jot it down. Okay, a little bit later, another one, jot it down, and then they start coming, these tightening in the stomach. And around 4 o'clock, I call up Manuel, who's on the other side of MIT in building 26 in the basement there. And I said, I think we ought to start thinking about going to the hospital, okay? So Manuel comes by. Let's see if I have this. And that's our blue Dodge Dart. And I get out of MIT on that right there, and then we get in the car and drive to Boston, okay? And then here we are going to Beth Israel Hospital. Okay, and then apparently obstetrics is on the top floor, so let's see, how am I going to go forward? Yeah, we're here, and I take the elevator up to the top floor and then over to where they put me. And it was a fairly, Manuel mentioned the CTM you're assuming it has a fairly easy birth, and we had a fairly easy birth as well. Actually, in those years, in the US, most women were anesthetized for birth. And I did not want that. I wanted to be present. So Manuel and I had done LeMay's crashes. And so we did, I was there very awake when Avram was born. And one of these startling memories of mine is that the nurse comes over to hand me this baby, and this little thing is looking all around the room. It's so alert. It was just looking at it, really sizing up. I don't want to embarrass him, but this is my strongest, one of my strongest memories, being up there in that hospital room. And I didn't have a picture of that. So I asked ChatGPT, so there were these bright eyes, to create a picture, okay, of that so I could show you. And this is the picture it created. Now, that's a hallucination, right? Because that's not a newborn baby, right? And whatever. But that was what ChatGPT gave me. And then I was thinking, how did I get that picture? Well, I had put a lot of my pictures to make a slideshow, which we'll see later, on the web, and I guess ChatGPT had seen it. And if you look at this arm over here, this little peculiar arm, and I thought, aha, that really came from this other picture that I had of Manuel with Avram. So that's what Chat did, actually. So that was our young kid. And you know, I was so excited to have this fantastic baby. And I was up all night, and because I'm on the top floor and there was this window, I had this light show all night long. You know, Boston was lighting up, and so it was like a fantastic celebration. And for me, that was really one of my memories. Okay, so you know, I was really surprised that you didn't come with a user manual at all. And I hadn't played with dolls when I was a kid. I was not so interested in dolls. So we needed to, Manuel and I needed to have some instruction, but of course, Avram was very humble and helpful, and even in those years, he helped us out. So we sort of figured it all out together. But actually, you know, that was timed pretty well. May 27th, we had the summer, more or less off. And then in the fall, we had to, you know, I was going back to graduate school, and Manuel was teaching, and we had to figure out what to do. But in those years, there was no daycare. Didn't hear, you know, women weren't working or whatever, no daycare. So we found this baby carrier, and here he is in my office in Building 2. And Avram came every place with us. We would take him around room to room. And here he is. Actually, one of the places was the basement of Building 26. That's Research Laboratory of Electronics, where Manuel had an office in Warren McCulloch's lab. So Avram spent some time there. You go around from my office to Manuel's office down in the basement. And then actually, it was quite remarkable. MIT has a room for women students right under the dome. It's really a fantastic room. And sometimes Avram would come with me there. And also some of our friends would come by. In particular, I remember Mitch Feigenbaum, who was a graduate student of physics then. He would come by, he loved playing with Avram and doing games. And here I think they're looking at string theory. This is way before it was really anybody even knew about string theory or knot theory or something like that. So obviously Avram had a very head start at MIT. You know, it was a little bit over the top preparation, but he was there for 2 years, and I got my PhD, and we came out to Berkeley then. So, but it paid off, because 25 years later, he got his own PhD at MIT with Franz. So that preparation. I was thinking it's a little over the top, because I know parents are doing a whole lot to get their kids into top schools. And I think we really went over the top with those first 2 years. But okay, he had a great thing. So happy birthday, Av. And you've brought so much joy and happiness to us. We were really like growing up as a kind of little team group. Okay, so actually I've changed my talk a little bit to look at, you know, my Manuel talked a lot about the Conscious Turing Machine, and I'd like to sort of put it in the landscape of consciousness science. So I'd like to try to do that. So because my talk overlaps with Manuel's a lot to get to this point, I decided I'm going to give you, can you give me a water? Someone give me a water, Alex. This is my grandson, Alex, Avram's son, Alex Blum. Thank you, Alex.
Blum to the fourth copy.
So you can see this is a whole family outfit enterprise. So what I'm going to go is right to the punchline in case I can't get to it. So where does, you might ask, where does this model, Conscious Turing Machine, fit into the whole landscape, and what is that landscape? Okay, so we have this formal, simple formal machine model, okay, and it turns out, and the punchline will be that the CTM aligns at the high level, at least with many of the major theories of consciousness. So you may have heard that there are many different theories of consciousness, or you may not have heard it, but it's actually in the news now, and there are different ones coming up. But there are about 5 or 10 major ones, and they're looking at different aspects of consciousness. And we seem to align with all the major ones. What's interesting is that there are two of the top ones, the global workspace, which Manuel had mentioned, and there's the version of global neuronal workspace theory, and integrated information theory. And these are sort of the two major theories. You might have heard about IIT, because Seth Aronson had had some controversy about that. That's one. And it measures, what that does is it's more of the, probably of all of these, is probably most mathematical. It has a measure which is called phi, which sort of measures the interconnectedness and the feedback of what's happening. And so, but these two theories are at loggerheads, and a while back, it's interesting, the Templeton Foundation supported research, which called collaborative adversarial collaboration, okay, to see which of those theories was right. And so they set up some experiments that they all agreed to, and so there was no consensus of what happened. But what happens is the global workspace sort of says consciousness is really located in the prefrontal cortex, and IIT says in the posterior cortex. Okay, so those experiments were set up to see where, in fact, things were happening. So people say, well, how could you be compatible with these two theories that are contradicting each other? And our answer is that the CTM, the Conscious Turing Machine, is not tied to any brain location. It abstracts functional properties. So that's the point. It's, in fact, abstracting functional properties. So we're saying that our machine has hi-fi. It has a lot of interconnectedness, and it has a lot of feedback. So if you were going to use IIT's measure, pretty high. And as you saw with Manuel, the global broadcasting is a big aspect of ours. So we're looking at functionality, not location, not aspects. So that's how we can do all that. So what I'd like to address is what is consciousness science, where does CTM fit in, and implications for AI. So so let me go back to where people are in consciousness science. Throughout the millennia, consciousness has been the purview of philosophers and theologians, and until about 35 years ago, the scientific study of consciousness was taboo, so it wasn't a scientific study. And now it is actively pursued by cognitive scientists, neuroscientists, psychologists, physicists, many people. So what happened? What changed? Well, one of the things that changed was the technology. In the 90s was the invention of fMRI technology, which allowed researchers to look at the head, when people were doing things non-invasively, so you could sort of see so crudely what was going on. So that was one of the technologies that helped change. And then in '95, Francis Crick, Nobel Prize winner for DNA, wrote this book, The Astonishing Hypothesis, where he advocated the scientific study of consciousness. And in fact, he said, he was advocating the neural correlates of consciousness, where in the brain were these things happening. And at the same time, Manuel had mentioned David Chalmers, who is a philosopher. And actually, he actually, I think, put a lot of things clearly. This is an area of consciousness all over the place. I think he clearly delineated the areas. So what David Chalmers does is he talked about consciousness in terms of the easy problems and the hard problems. And what he says is the easy problems of consciousness are those that seem directly susceptible to the standard methods of cognitive science, whereby a phenomena is explained in terms of computational or neural mechanisms. So that part, the attention, it's also often called functional consciousness, access consciousness, and what Manuel talked about, that's what we call conscious attention, when all the processors receive the winning broadcast. Okay, and so that's the global broadcast in our model. And the hard problem, the really hard problem of consciousness is the problem of experience, where when we think and perceive, there's a whir of information processing, but there's also a subjective aspect, and it's often called subjective or phenomenal consciousness, and we call that conscious awareness. And that comes in when our machine self-generates its internal language, its multisensory internal language, brainish, and the co-evolvement with the model of the world. And in consciousness science, this phenomenal consciousness is usually associated with qualia, the feeling of what it is like, and that goes back to Thomas Nagel's paper in '74 when he asked, what is it like to be a bat? How could we know what it likes to be a bat? And many focus on what it feels like when you see red. And I think that's a big thing to focus. What do you feel like when you see red? Hot. You know, it seems to me that it's also very cultural, whether you come from China, US, what you associate red with, and different things. But anyway, that's often what people who study consciousness look at in terms of phenomenal consciousness. And many view the hard problem as needing a new kind of science to explain subjective consciousness. And as you saw with Manuel, we view the hard problem as a challenge to show that phenomenal consciousness or the subjective consciousness is surely computational. So that's where we're coming from, and that's coming from the coevolution of brainish and the model of the world. And of course, we're inspired by Alan Turing's simple model of computation and Bernard Baars' global workspace theory. I won't go into that. And I'm going to go through some of this first part very, very quickly. I can't talk as fast as you, Nina, but let me try. But what I want to say to start is that the Conscious Turing Machine, it's not a standard Turing machine, and I'll mention that. And the feeling of consciousness doesn't come from its input-output map, or its computing power. It's what's under the hood. It's how it's operating is why what we're saying is where the consciousness comes from. And it's not a standard global workspace, and as Manuel said, first of all, it's a formal model, and it has a well-defined competition, and there's no central executive. And it's subjective feelings, which Baars doesn't have. Baars has mainly the broadcast. We're saying our machine also needs to be developing its self-generated language, which fuses together many of the sensibilities, seeing and hearing and sight and touch and all of that, fusing the sensibilities together in one brainish word as it's developing its model of the world. And of course, we want to say that the CTM is not a model of the brain. It's way too simple for that. And again, we're not looking at any particular location of the brain. So I want to go very quickly over the first two parts, because it's really repetition of what Manuel has talked about, and then go a little bit more into the third part. So let's see. Here's the specs of the CTM, and you've seen that. And here's our picture. Here's my cartoon picture of it, and you can see the STM. It's a broadcasting station. That's the stage, and the long-term memory processors down below, and we're assuming a whole lot. We're assuming about 2 to the 24th or 10 to the 7th. A little mistake there in terms of we were saying that there were 10 to the 7th cortical columns, but maybe 10 to the 6th cortical columns, yeah. Okay, those processors start out, it's very important, they're mostly generic. They're powerful, but generic. And their functionalities will depend on experience, but we do have built-in ones. And there's the input processors. Those are the ones that's like sensory processors that have to input from the outside world. We have output processors, which send signals to actuators to affect the outside world. And we have these homeostats, which are called gauge processors, which really trigger initial action. So these homeostats are really what triggers some kind of the need to live or the will to live. We don't have very many of them, but those are the initial triggers. They're very important. Manuel talked about the oxygen gauge. Fuel gauge is another one. And unlinked at the beginning, and we have predictive learning algorithms, particularly Avram's sleeping expert algorithms built into the processors. And each processor has its own internal language, but it has Brainish. Brainish is being developed. So a Brainish label for a rose will be a fusion of the red color of the rose and the sweet smell of the rose and the soft touch of the petal. So a Brainish word fuses different sensibilities, different modalities. And we have the up tree, which is the conduit for the competition, and then we'll talk about that, where you each processor puts at every moment of time chunks of information that they want to get out onto stage, and we have the competition. And very importantly is in the literature, people talk about chunks of information. This goes way back to the 50s, the chunks, but nobody's ever defines it. So again, in our formal model, we have a formal notion of chunk in our model, which is this 4+ tuple. And very importantly is that gist, which is a succinct bit of information in Brainish. So like, as Manuel said, a frame in a dream. And actually, an interesting way to think about consciousness as being computational in here is if you think of your dreams at night, right? You're shut off from the world. But you see things very strongly, and you feel things. You've had nightmares, right? You're feeling things right in your head. You're constructing it right up here. So this gists are really very much like what's happening in terms of frames in the dream. Okay, that's important. And then the down tree, and then conduit for global. And then as chunks get broadcast, all the processors save all the chunks, so they all have a common dictionary, and the first two components of the chunks are the words. We have a heavy and light principle to get the links, and yeah, so what links do is they turn slow conscious communication into fast communication. So when you're starting to ride a bike, you're thinking, right, of all your movements, you're really having to think about it. But after a while, as the links form between your motor processors and your vision and all that, you can then, with the links, basically ride a bike unconsciously until something happens. And really importantly in our model, which is not in some of the other models, is it's not a brain in the vat. So when we're looking at the CTM, it's very much having inputs coming from the outside world through sensors, and it's going to sensory processors, and it's very much affecting the outside world with its motor processes affecting actuators that move around in the world. So this is a very important aspect of the embodiment and embeddedment, enactment in the world, which are ideas that come up a lot in consciousness science, and we really need to have that in our machines. So very important, not a brain in a vat. And so there's this much predictive dynamics going on. Prediction is very important, feedback and learning. in our machine. As Manuel said, conscious attention is the reception by all processes of the global broadcast. And what's interesting here is a couple of things. The winning chunk, when it's broadcast down, it actually has some auxiliary information, which is about, it's gathering, as the chunk is winning, it's gathering more and more global information. So when the chunk is broadcast down, every processor sees the following. They know what processor won, right? They know what the gist was that won. They know what the weight was, whether it's positive, negative, or how much was in. So they're getting a lot of information, and they're also getting global information of what's happening at large, which they didn't have. And somebody asked about this. These processors don't know everything. They're just local. They're communicating very locally at first. So they don't have global information, but they will get global information from the broadcast. So they're getting quite a lot of information there. And in fact, immediately we can see one of these phenomena that people who study consciousness, this thing called the Libet effect, which you might have heard of, is that the idea that you actually are only conscious of the decisions you made after, maybe 250 milliseconds after you've made it. And you can see what's happening here in the CTM. So the winning chunk, which comes out, so at time t it's put in, it wins, it goes h steps up, wins, and then one more down, it gets projected. So it's h plus 1 steps later when we really find out about what decision really won, even though that decision was put in h plus 1 time earlier. So there is a delay, and if the ticks are right, it does come out to something order of magnitude 250 milliseconds before you're paying conscious attention to a decision that was made before. Okay, so that's one thing that comes out of the model, that there is, in our model at least, there is that delay between decision made and your conscious attention of it. And that's, Manuel talked about one of our first axioms, the global broadcast axiom that evokes a unitary experience. And so the reasonable error definition lies in the number of phenomena associated with consciousness that the model can exhibit and explain easily and naturally, and agrees at the high level. So what I decided to do right now is I put back in some slides, which I'll give, and I won't go into a lot of the stuff about the world models that I was going to do. And then I'm saying, yeah. So what I'm going to do is give you some examples, which I think are kind of fun, to see how our machine, the CTM, can experience certain phenomena that scientists associate with consciousness. So I mentioned Libet effect, and now I'm going to go into blind sight, inattentional blindness, and change blindness. So I'm going to give you 3 examples, and then I'm going to skip over to the end. So, okay, so these are 3 examples. So the first example I'm going to give is something called blind sight. And blind sight is a case when people claim they're blind, but nevertheless, they can maneuver around a complicated room, okay? So here we have a man or a CTM, and he's asked to go to the other room, and he says, but I can't see. And nevertheless, he gets up, walks to the door, avoiding obstacles, okay? So what's going on? So I'll give you the CTM explanation. Okay, so here's our CTM explanation. The vision processor, so information's coming in through the eye to the vision processor, and it works properly, and there's been a link formed between the vision processor and the motor processor. Okay, that's happened earlier on, and it sends via the link to the motor processor, move to the other room. Okay, so the guy does that. But what we're claiming is that there's something missing, that the information from the vision processor somehow isn't getting up to STM. Maybe a link is broken, or it's not giving enough weight or something. So the information isn't directly going from vision to short-term memory, so it's not getting broadcast. So the Conscious Turing Machine can't pay conscious attention, even though it's doing some of, it's walking around this room. It's not going to be perfect, but it can do some things via links. So our hypothesis here is that the connections to the short-term memory is damaged, but partial processes links are functioning. And this agrees at the high level with some of the neuroscience literature. And what we're predicting here is that blind sight requires prior sight, because in our model, it required link forming, and that link would have formed but if it had prior sight. And I've asked a lot of neuroscientists who've worked on blind sight, do you have any cases at all of a person with blind sight that wasn't cited earlier? And they don't have a single case, so I'm looking for that to see about our hypothesis, so here. And unintentional blindness, so the next two examples are ones that are often given psychology classes, and you may have seen this film where the viewers are asked to count how many times white-shirted players pass the ball, and they're pretty good at this. They say 15. Okay, but the thing is, did you see the gorilla? Okay, here's the gorilla. I don't know if you saw it here in plain sight, okay? And so what's going on in terms of the CTM explanation? Well, in the CTM, we are given a task to look for. Higher weights are given to that task, and we might not be conscious of other things in the picture that have lower weights. So in other words, white-shirted, when the vision comes in with white-shirted chunks, that processors are putting very high weights on that because they're looking for that. And the black-shirted processors are getting very low weights, and in particular the gorilla is getting very low weights, so it doesn't get up to consciousness. So the explanation in our model is that the weights are playing a role here. And that again, corresponds to, aligns with some of the literature. And then this final one that I'll give on change blindness, which again you may have seen on the internet, which I think is also fun, and we'll see our explanation. So here you have a detective coming into a room, and he sees a dead guy on the floor. Okay, and he immediately says, clearly somebody in this room murdered Lord Smythe, each of you tell me your whereabouts. Okay, and then he goes and interrogates everybody, and the maid says, I was polishing the brass in the master bedroom, and the butler said I was buttering his lordship's scones, and Lady Smythe says I was planting my petunias in the potting shed, and immediately there's very sharp detective says, Constable, arrest Lady Smythe. Okay, and she says, but how did you know? And he says, Madam, as any horticulturist will tell you, one does not plant petunias until May. But how observant were you? Okay, here, this is the final scene, okay? And this is the initial scene. And look, the detective has changed his coat, and the flowers have changed, and the dead guy also changed his clothes and his knees up, right? And there's almost everything in that object, and that scene has changed. Okay, what's going on? Why didn't we or the CTM see the many changes? And we'll say, there's the same gist explained the first scene and the last scene. The scene is the living room of a mansion with butler, maid, and detective, and a man laid out on the floor. And that's all the information you could keep over that time period with these interrogations in your head. So that's, again, the succinctness of the gist, and the fact that we can only hold a little bit of information up in short-term memory at any time is our explanation. And again, that agrees with some of the stuff in the neuroscience literature. Okay, so I'm going to keep on, I'm not going to go through all of this, the development of the model of the world, but I would say that one of our things is attention is not all you need, and I think that's a message to the people up in AI, and that's where we need the coevolution of brainish and the model of the world for the subjective consciousness. Okay, and I'm not going to go into details because Manuel did. Here I have models of the world here and all of this. One thing, here's a baby discovering its left leg, and in its model of the world, that's self, and that's going on. And then we have this baby who starts out with a very foggy model of the world, and then starts getting a couple of words, like blob zero is its first word for its blob, and pain, as Manuel said, is one of its next words, and then you can put these two words together and get that blob zero is in pain, one of the first brainish sentences. You can start putting these words together, and these words evolve over time. Interesting, if you want to bring this back to human situation, consequences of mislabeling from human experiences, Cotard syndrome is one where people think they're dead, and that's where in their brainish, in their model of the world, they've labeled somehow themselves dead. And body integrity disorder, where some people think that their limb doesn't belong to them and they want to get it cut off, and no doctor will do it. They'll go someplace else, get that limb cut off, and they're very happy. And the opposite is that phantom limb syndrome, when the limb is cut off and those people still feel it itching and hurting, that's because it's still labeled self in the brain. Okay, so I'm not going to go. We have the two axioms, the global broadcast axiom, which is basically saying that the broadcast gives you a unitary experience, and the global unpacking axiom, which is for subjective consciousness, that when you start to unpack the brainish words, you get a unique fusion of the subjective experience evoked by the meanings, and these are sort of very inductive. It starts with the primal, as Manuel said, and it's built up inductively, these feelings. Okay, I'm not going to do that, and I'm going to go ahead. So this is the final slide in the sense that the alignment with the key the Conscious Turing Machine, as I said, aligns with the key principles. Of course, the global workspace, because that's what we were inspired by, but all of these are the major ones that I've put up here and on various levels. And in particular, this one, the EEE one, is very important. This is a very important one in the consciousness science, and because the CTM is in the world, it does experience many of these phenomena. So, and Manuel mentioned Kevin Mitchell, who a couple of years ago put on his blog the 15, actually each question has 3 parts, and we took it as a challenge to go through the CTM and answer all of these questions from the perspective of the CTM, and you can read that on our archive paper. Predictions, no central executive, the classic studies, and people are starting to see, actually, a paper just came out last fall saying that even though everybody has predicted the central executive, they never found it, and we're now saying, the neuroscientists are saying that there's no central executive. Clinical, Manuel mentioned pain asymbolia, and I mentioned blind sight requires prior sight, dreaming as a test for consciousness. And to end, we have a simple formal machine model, which is clearly buildable and at a high level exhibits and explains phenomena associated with human consciousness, aligns and integrates underlying principles of major theories, and addresses questions that a theory of consciousness should encompass. So our conclusion is that AI consciousness is ineffable. That's it. Okay, thank you.
Running a little late, maybe one question.
Any questions? Dana.
Sure.
Okay.
Question I have is whether how you weight the various ideas of consciousness as to being either an explanation for the biology that we see. For example, I don't know, you seem to do a lot of that. For example, the blindsidedness business, I don't know if the other animals have blindsidedness or not, but, you know, you try to explain that and have a model that incorporates some of that.
Yeah, so in fact, blindsight was first discovered in animals.
Oh, okay.
Yeah,
I
actually.
don't know the literature.
Yeah.
But how much of the weight you would put on that versus how much weight you would put on saying, you know, does this model capture the primary goals of what I'm looking for in terms of a model of consciousness, and the principles come first?
Well, the way I see it is many of these different theories are looking at different aspects of consciousness. That's sort of different parts of the elephant, okay? And many of them are saying, well, this is the most important one, or that is the most important one, or that is the most important. And I think what we're saying, we align with practically all of the major theories, but the important ones for us are the broadcast one and building the model of the world. And I think that's starting to become very much part of the scene, that the model of the world, and I don't think anybody's talked about brainish, this multisensory language that's self-generated. It's not put into the machine, it's not put into the language. The machine itself is generating this language from its own experiences, and we're saying that that part, this model of the world, self-generated, is very important. And that aligns a lot with evolutionary theories of consciousness as well. So we can tie things.
Biology is the more important one.
Okay, I don't want to get into this, but there is a controversy, of course. We were, you know, computer scientists, and we think things are computational in our way. And right now, there's the group in the consciousness science who are saying biological naturalism. It's something that many people want to hear, that it has to be a biological entity. And that's getting a little bit of attention now. I think a book just came out, a popular book, whatever. So I think that the people want to believe that we're the center of the universe, right? And I think that's touching a lot of people. And there is a kind of controversy. Does this TCS, do you need it? And actually, this is for all of you here, everybody, we have these big debates all the time with neuroscientists saying, you need to have oscillations, or you need to have an analog computation, or you need to have quantum collapse, or you need to have all these other kinds of methods of computation. And we're trying to say, well, most of those, you know, whatever you're telling us, you know, the Turing type of computation is as powerful. And that's, I think, the big debate between our approach and the way the biologists and neuroscientists are looking at it. And almost every day on Blue Sky, I'm having a debate with Earl Miller at MIT, who's pointing out every day, you know, I believe oscillations are a means of computation. But that doesn't mean you need oscillations for consciousness, okay? So a lot of issues here, and I could use all your help in, I wouldn't say in defending this approach, but in giving more insights why a computational approach is viable. And we think our machine is doing that. But Ron, we took up a lot of your time, and you're a key person here in our lives. And I want to thank you so much. And right next to Ron, I want to just mention Chuck Eng. And you might have noted that at the beginning I said we were being supported by SAIR. That's Science and AI for Research. And Chuck and Terry Tao are co-directors of this new organization, which is looking at how AI can help scientific research. So thanks, Chuck, for supporting us as well. Thanks for being here. Okay.
All right, sorry.